So today we're going to get a sneak peek into a second type of calculus word problem, which are optimization problems. So we've calculated the derivative, we've seen how it can classify local maxes or mins, and those local max and min values are really important in solving real life problems. So if you think of any company, they're trying to maximize their profit but minimize their cost. They're trying to make a certain vessel to minimize the cost for production. Maybe you're given a certain amount of fencing and you need to close in a specific area. So calculus is littered across all different disciplines without really knowing that you need to use it. So what we want to go through today is kind of how can I go about solving these optimization problems, and how do I utilize this concept of a max and min to optimize something. So we want to go through a strategy first for solving these, because of course word problems always seem to be the most difficult because there's a lot going on. First thing you want to do is understand the problem. And I know that's kind of trivial to say, but what you really want to pick is what's given to you and what's unknown. So what is the thing that you are searching for? If possible, you want to draw a diagram. So if you're dealing with some type of fencing, if you're dealing with a box, if you're dealing with a frame of some sort, draw a picture so this way you're able to label it and you're able to keep track of all of your pieces. You're going to have variables, so you're having unknowns. You want to introduce notation, and there's likely multiple unknown variables: volume, area, length, width, height. There could be many things that you don't know what the quantities need to be. So you want to make a list of appropriate variables for their unknown quantities. So don't be calling area V. Use something that makes sense. You can use X, Y, Z if you're dealing with like lengths and stuff, because I know L can get a little fuzzy too, but just don't give it anything in left field. If there is something that is always a constant, absolutely put that number in. So you were told you have 500 feet of fencing. That's not going to change. You don't need to say your perimeter is a variable P. Perimeter is set, it's 500. Once you've made that notation, label your drawing. Because if I don't know what these pieces are representing, there's no way that I'm going to be able to understand what you're doing. Now, you have some quantity you're trying to optimize, whether that be I'm optimizing the area of this rectangle given a particular perimeter. So you want to express the quantity you're trying to optimize in terms of my other variables and constants we've assigned. The problem is, think of area, it deals with a length and a width. Maybe they're both unknown. So what happens when you have multiple variables? You don't know how to deal with multivariate functions unless you have to go on to Calc 3. So if there are multiple variables on one side of the equation, you need to somehow rewrite this thing you're optimizing in terms of a single variable using your given information. You're going to be able to turn this multivariable thing into a single variable thing, which we now will know how to take a derivative of. Once you've done that, you're going to find the absolute max or mins using the method from the previous section. The problem is absolute max and mins are quite difficult because if I'm dealing with an infinite length, I only know how to find absolute max and min on a closed interval using that closed interval method. So really we have another test that's going to be useful for finding these absolute extrema. And so this is called the first derivative test for absolute extrema. So this states, suppose that C is a critical number of a continuous function on an interval. Basically, if it's the only critical number and it's going to swap from increasing or decreasing, or vice versa from decreasing to increasing, you can classify it as an absolute extrema. So if your derivative is positive on the left half of your critical number, so that means it's increasing up to C, and the derivative is negative after C, so it's decreasing after that point, that is the only classification that you have for these. It's always increasing up to C, always decreasing after that. Then this y value corresponding to C will be your absolute max value. If the reverse happens, so if the derivative is negative on the left, it's decreasing up to that point. derivative is positive on the right, it's increasing after that, then f of c is going to be your absolute minimum value. And so to kind of just see these graphically, in the first case, you're increasing up to this value and decreasing after it. And I'm never going to turn around because my derivative is not going to change signs on either sides of these. So I've got that absolute maximum. And in the other case, I'm decreasing always down to c, and then I increase always after that. So we have an absolute minimum. So the first example we're going to try is we are told a lifeguard needs to rope off a rectangular swimming area on the beach using 180 yards of rope. What dimensions of the rectangle will maximize the area? So we're given a little note that the shoreline is going to be one of the sides. So before I do anything, I want to draw a picture of what's going on. We've got our beach right here. So our water is over here that we need to rope off. And we're going to block off one side, two side, three side. So we definitely do not need to block off that third because that's going to make it so that I can't even get into the swimming water. So no rope is going to be needed on this side. So if this is a rectangle, those two sides would be x, this side would be y. And our goal is we want to maximize the area. But in terms of our variables, our area is x times y. And this is that problem. I can't find a derivative of this because I have two unknown variables, x and y. So our area is x times y. But I do have another piece of information that was given to us that we haven't used. We have 180 yards of rope. And that would represent the perimeter. So basically this side plus this one has to equal 180. So that's going to be how we're able to rewrite this multivariable equation in terms of a single variable. Okay. So we need to rewrite the area purely in terms of x or y, okay? And so going back up to this given information, we can say 180 is y plus 2x because we have two sides of length x. So using the given info, we have 2x plus y is 180. I can easily solve that for y. That's 180 minus 2x. So instead of writing y up here, I can say this side is 180 minus 2x. So ultimately, the area is A, which is x times y, which now knowing y is 180 minus 2x, we can go ahead and plug that here. And so our area is 180x minus 2x squared. Okay? And now I have a single variable function for this area that I'm trying to maximize. So we want to find the absolute max of A. So that requires us taking a derivative, which would be 180 minus 4x. We go ahead and set that equal to 0. And this is 180 is equal to 4x. Dividing by 4 would give us x is equal to 45. Okay. So I have a single critical number. It's likely going to be an absolute maximum, but we do want to check that's the case. So utilizing our lovely number lines, we're working with the derivative. 45 is my only important number I found. This is also dealing with a length, so I'm not going to make a length that's less than 0. So if we go ahead and plug in different values for this derivative, if you think of plugging in 1, that would be 180 minus 4. It's going to be positive on this side. If I plug in like 50, that would be 180 minus 200. The derivative will be negative on this side. So we are increasing up to that point, decreasing afterwards. So indeed, it is an absolute max. So I should make my x back up here equal to 45 yards. And then I can go ahead and plug 45 in to figure out what y would equal, which we're going to see in a second will be 90 yards. Okay. So the dimensions of the swimming area that will maximize the area are, our x value is 45 yards. Our y value is 180 minus 2 times x. So that's 180 minus 90, which gives us 90 yards. Okay. So ultimately, the lifeguard should rope off a rectangle with dimensions 45 yards by 90 yards. And if I go back up to my question, that does indeed answer it. What dimensions will maximize the area? If it asked for the maximum area, you could just multiply it, so 45 times 90, and you would see the maximum swimming area would be like 4,050 yards, okay? But this is all it looked for, just the dimensions of the maximum swimming area. Let's try a second one. We are told 1,200 centimeters squared of material is available to make a box with a square base and an open top. We want to find the largest possible volume of the box. So again, I'm going to draw a picture first. We've got our box. This is a square base, so all sides are exactly the same, and I have no top to this. So if I want to give some values, I'll call this B for the base. Both sides are going to be exactly the same because it's square. My height of the box, no idea what that is. And our goal is to find the largest possible volume of the box. So to write that in terms of these variables, we want to maximize the volume. And in this case, the volume is length times width times height. So the volume is b squared times h. Again, I can't take a derivative yet because I don't have a single variable function. So that's where I need to go back and use this other piece of information. We're given 1,200 centimeters squared of material. And so this is basically going to represent the surface area. Okay. So utilizing our variables, 1200 is going to be the area of the base, and the area of the base would be b squared. And then we're going to have 4 different sides. This front side here would be b times h. The side here, b times h. The back is b times h. And this other side is also b times h. So we have 4 sides that have area b times h. You have no top, so you don't need to worry about this piece up here. All right. So with that piece of information, again, I can rewrite v in terms of one variable. So we can solve the given info for h. That's probably going to be our easiest variable to deal with. So we've got 1200 is equal to b squared minus plus 4bh. Subtract the b squared to give us 1200 minus b squared is 4bh. Divide by 4b to give us 1200 minus b squared over 4b is h. And now in our volume formula, I'm going to go ahead and input this quantity that deals just with B's. So the volume of the box is V equals B squared times H, but we just figured out that H is 1200 minus b squared divided by 4b. So we got some simplification. One of these b's is going to cancel. So our volume is b times 1200 minus b squared over 4. Distributing out that b will be 1200b minus b cubed over 4. And I want to take a derivative, so I might as well divide each of these by 4. That's 300b minus 1/4 b cubed. So I want to maximize this. We go ahead and find those critical numbers. So I need to take a derivative. That will give us 300 minus 3/4 b squared. Want to set this thing equal to 0. So that gives us 300 equals 3/4 b squared. Now we can go ahead and multiply both sides by 4 to wipe part of the fraction. So 1200 is 3b squared. Divide by 3 to give us 400 is b squared. And then take square roots, but remember when you take a square root, you get a plus or minus. And the square root of 400 is 20. But b is representing a length, so you really only get one critical number because there's no negative lengths. Okay. So we have a single critical number. We want to go ahead and check it's a maximum. So we've got our number line, 20 is our only critical number. We're not going to have a length for a side that's negative. And we want to go ahead and see what is v prime equal to, which is 300 minus 3/4 b squared. So if we plug in 1, that would be 300 minus 3/4 times 1. Definitely positive over here, which in turn means we're increasing up to 20. If I plug in something on this side, think of plugging in 100 for the length. 300 minus 3/4 times 10,000. going to be huge, definitely going to be negative on this side. So my graph will be decreasing afterwards. And there's no other critical number that makes sense. So ultimately, there is an absolute max. When b equals 20. And then our unit in this case is centimeters. Okay. And all I want to answer is what is the largest possible volume of the box. My volume is solely in terms of b, so I just go ahead and plug 20 into here to get the volume of our largest box. So the volume of the largest box is V. It's 300B minus 1/4 B cubed. Plugging in our absolute max will give us 300 times 20 minus 1/4 times 20 cubed. And if you go ahead and go through that, you'll see this is 4,000 and our units are centimeters cubed. So if I'm given 1,200 centimeters squared of material for a box with a square base, the biggest volume I can possibly have is 4,000 centimeters cubed. So I got one last example to go through. This one's definitely the most difficult of them all. We want to find the points on the ellipse, which is 4x squared plus y squared equals 4, that are furthest away from the point 1, 0. So before I even try to go about what we need to do, let's draw this ellipse so we can get an idea of what's going on. If you remember anything about your ellipses, you need a 1 on this side, so everything has to be divided by 4, which means the 4 in front of the x would cancel. And what this tells you is how far in the x and y direction you go. So 1 is under x. I'm going to go 1 in the x direction. 4 is under y. Remember, you're going a square root. So you go 2 in the y direction. So to graph our ellipse, we're going to go through all of these different points. So 1 point here, 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 and here. We want to be the farthest we can from this point 1, 0. And because of the symmetry on the ellipse, there's going to be 2 points that happens for. So 1 will be all the way on this side. The other will be down here, and it'll have a symmetric distance. So my goal is to maximize the distance d, which is the point from 1, 0 to this arbitrary point xy. So let's write that out. Our goal is to maximize the distance d. And using our distance formula, the distance is the square root of the difference in x's squared plus the difference in y values squared. So I look at the difference in x and 1, y and 0, where x and y is on the ellipse. Okay. But I know I'm going to have to take a derivative. I really don't want the square root. I'm going to go ahead and call capital D the distance squared to get rid of that square root. Okay. Because maximizing capital D is the same as maximizing little d. And it's much easier to work with. Because I just need to find the points. I don't need to find the actual distance between them. And if I'm trying to take a derivative without a square root, it's much better. But getting rid of the square root doesn't change the fact that you're maximizing the thing underneath it. But again, the problem is I have two variables, so I can't take a derivative yet. But I know this point xy has to be on the ellipse. So I need to solve for one of these variables. And if you notice, y squared appears in the equation of the ellipse. So I can easily solve for y squared. So since xy is a point on the ellipse, it must satisfy that 4x squared plus y squared is equal to 4. Or solving for y squared, that must equal 4 minus x squared. And now, instead of this y squared, I can replace it by this quantity, and now I totally have just x's and can take derivatives. Okay. So plugging this into D gives us the distance squared is x minus 1 squared plus y squared. But y squared we just figured out must equal 4 minus 4x squared. So we need to FOIL this out because I've got to take a derivative. That'll be x squared minus 2x plus 1 plus 4 minus 4x squared. Grouping my like terms, I've got x squared minus 4x squared, so negative 3x squared, minus 2x plus 5. And now I have a single variable function for my distance. We want to go ahead and find those critical numbers. And so this gives us d prime is negative 6x minus 2. We want that to equal 0. So negative 6x is positive 2, or x is negative 2 divided by 6, which is negative 1/3. And we need to show it's a maximum by plugging stuff into our derivative. So if I plug negative 1, that will be positive 6 minus 2. So my derivative will be positive on this side. If I plug in 0, that'll give me negative 2, negative on this side. So it's increasing to decreasing, so indeed it is. Okay. And so this is our absolute maximum. We need to actually find the points. Okay. So we are asked, what are the points on the ellipse furthest away from 1, 0? So we have our x-coordinate is negative 1/3. We need to find our y-coordinates. And we know y squared is 4 minus 4x squared by solving for that ellipse. So y squared is 4 minus 4 times negative 1/3 squared, which would be 4 minus 4 times 1/9. Rewriting 4 in terms of 9, because this is negative 4 over 9, would be 36 over 9. So this fraction becomes 32 over 9. And so our y values are the square root of 32 over 9. But remember, we get plus or minus. You can take the square root of each individually. So you get root 32 up top, 3 in the bottom. And if you do want to simplify that or need to rationalize it, you can write 32 as 4 times 8, but that can be simplified more. 16 times 2. And then the square root of 16 is 4. So you get 4 root 2 over 3. So the points would be negative 1/3, positive 4 root 2 over 3, and negative 1/3, negative 4 root 2 over 3. So we knew at the very beginning that we'd have two different points because of the symmetry, one in the top, one in the bottom. So that might help you if you forget to put this plus or minus when you take a square root. But that is it for section 3.7 and our optimization problems. Definitely take your time with these. You are always going to be doing this process where you're coming up with some multivariable function because you've got a couple unknowns and you have to use some given constraint to rewrite that multivariable equation in terms of just one thing.